Hello, this is a solution to the categories now we try. Here I asked you to make a category where the objects are preorders and the morphisms are monotone maps. So let's do that. So the easy way to do this is to use co-pattern matching. So I'm going to split on the result, and then I have to say what the objects, the homomorphisms, and the identity, composition, and the laws are for this category. So for the objects, I have to give a set, and I want it to be the set of preorders that are defined above. I think it's with the lowercase o. And I also said that I wanted the morphisms to be exactly the monotone maps. So we see that that has the right type, because given two preorders P and Q, we're going to get a large set of morphisms between them. So that's going to fit right in here. And then we have to give an identity. And again, we can use co-pattern matching to give a monotone map, because a monotone map is given by a function between the carriers. So that's the underlying sets. And the proof that this map is monotone, so that if x is less than y, then the result of the function applied to x is less than the result of the function applied to y. So first we have to give the underlying function for the identity. Well, that should be a function from a to a. Just going to be the identity function, and then here we have to prove that this function is monotone. So that means that if given x and y and a proof that x is smaller than y, we have to produce a proof that x is smaller than y, because that's the result of applying this function to x and then to y. Right? So that's going to be the same proof p. Okay, for composition, we are we are given two monotone maps f and g, and we have to define their composite. So again, we first define the underlying function. That's going to be a function which goes from the carrier of a to the carrier of c. So we get given something in a, and we have to produce something in c. Well, we can look at the underlying function of g. That's going to take us from b to c. So if we just had a way to get to b, but the function f takes us from a to b, right? So we can give that the a. And now I have to show that this is monotone. So that means we're given x and y in a, proof p that x is smaller than y, and we have to show that all of this applied to x is smaller than all of this applied to y. But we know that f and g are monotone, so what are we doing first? Well, first we're applying f here. So if we look at the monotonicity proof for f and x and y, and if we give that p, that's going to tell us that f of x is smaller than f of y. So if we take that proof and we give it to the monotonicity proof of g, two things I can't bother to name, is going to be fun f of x and fun f of y, then that should exactly give us what we need. So again, it's really the composition of the monotonicity proofs here. Right? Okay, and then we have to show that this composition is associative, meaning that it doesn't matter how we bracket it. But we have this handy thing here for showing that two monotone maps are equal, saying that it's enough if the underlying functions are equal. Right? So if we use that, because here we really want to show that two compositions, that is two monotone maps, are equal, right? So that apply to something, it's going to give us what we need. So here we just need that the underlying maps are equal, but because these are just lambda expressions, it doesn't matter which way we bracket them. This is just equal by REFL. Similarly here for the identities, well, we want to show that two monotone maps are equal, so we can do that with this handy thing. It's going to be the same thing on the other side, and again, these are going to be easy. These are all just REFL. That's it. So that's the exercise.